everybody. Let's talk about acidity of carboxylic acids. And here you see a general acid deprotonation reaction equation. And for a generalized acid, it deprotonates in water and generating the corresponding conjugate base. Water here acts as Bronsted-Lowry base. After deprotonating, the acid itself turns into the hydronium ion. We can describe the equilibrium for this equation as the concentration of hydronium ion times the concentration of conjugate base divided by the concentration of the conjugate acid. For stronger acid, the stronger acid, the greater the Ka value. And we could also consider that for stronger acid, it tends to deprotonate further to generate more hydronium ion and the conjugate base. And in chemistry, we also tend to define the pKa as negative log of Ka. Okay, turns out that because for various compounds, the Ka value could vary drastically from 10 to the negative 50s to 10 to the positive 11th and 13th, and therefore pKa value turns out to be even more convenient. So one thing I want to emphasize, the stronger the acid, the greater the Ka, and the smaller the pKa. This page is from your handout, and on this page, I listed a number of the aqueous acidities of the different aliphatic acids. Okay, start with acetic acid with a pKa of 4.75, and many of the substituted acetic acids with a lower pKa or indicating stronger acids, and also with the butyric acid along with some substituted butyric acid. Okay, and we will talk more about this data after we're discussing some more in-depth reasoning associated to under what circumstances an acid is stronger than the other. Back to the general equation for the acid deprotonation reaction, we can describe the equilibrium for this equation. And this Ka value or the strength of an acid is really could be determined using some thermodynamic terms. Let's take a look. So one of the most important thermodynamic equation is the delta G equals negative RT ln Ka, natural log here, okay? To convert natural log to the 10-based log, and we can rewrite the equation as delta G equals negative 2.303 RT log Ka. Okay, so at 25 degrees C, we can plug in the value of R, that would be 8.314, and T would be 298 K, and the delta G eventually can be calculated as that is equals negative 5.7 log Ka in the case that delta G value is calculated in kilojoule per mole. Okay, and earlier, as I mentioned, that we like to use pKa instead of log Ka, so we can plug in pKa to replace the negative log Ka, so delta G can be written as 5.7 pKa. So delta G is directly proportional to pKa. Okay, and if we describe the delta G value with the unit of kilocal per mole, delta G naught equals 1.36 pKa. The reason I'm showing you this is because we will going to look at a number of the acetic acids, okay, the halogenated acetic acids, and we will compare the pKa of these acids and looking at the delta G of this, and also relate delta G with delta H and delta S. We know delta G equals delta H minus T delta S. That's the definition of delta G. Okay, so delta H is the enthalpy, and in terms of a particular molecule, it describes the stability of a molecule. Delta S is the measurement of disorderness. And so when we are looking at delta G, delta H, and delta S for the acid deprotonation reaction, we're looking at these thermodynamic terms for the overall reaction. Okay, so show you some interesting data here. Okay, as I mentioned that we also see on the previous handout, the pKa value of various carboxylic acids are different, okay, and the fluoroacetic acid has the lowest pKa, indicates fluoroacetic acid is the strongest in aqueous solution, okay, and the acetic acid is also listed here as a reference. It should be 4.75, depends on who reports the data. And so over here, the delta G value and delta H and delta S value together shows that this pKa is determined by both delta H and delta S of the acid deprotonation process, okay, and they both contribute drastically to this, okay. And earlier and when we talk about acidity in many of the other chapters, we often look at the stability of the conjugate base. And because the more stable the conjugate base, the greater the Ka value and the stronger the acid. Okay, so in terms of the halogenated acetic acid, in aqueous solution, the stability of the conjugate base is essentially determined by the electronegativity of the halogen, or determined by the inductive effect of the halogen. Those halogens are inductively electron withdrawing group and stabilize the negative charged conjugate base, the corresponding acetate, right? And if I'm writing a acid deprotonation reaction, I'm indicating the conjugate base acetate. We know that acetate is a negative charged. So when you have a halogen that bonded to the alpha carbon, the halogen is electron withdrawing group, can help stabilize the negative charged acetate. Okay, so in aqueous solution, we can conclude that the acidity increased from bromo to chloro to fluoroacetic acid, and because the electronegativity plays very important role. Okay, and I have this written, I have the statement written. See if we can show it in the page. Okay, we could. All right, and you may notice that in some other literature or books, you may see analysis in terms of how the acids and the acetates, the conjugate base, interact with the solvent, and how the solvation is playing a role. Really, when the solvation plays a role, it really plays a role in terms of the delta S value. We're not going to look at each individual intermolecular interaction. For this case, I just want to give you some general sense in terms of how this different thermodynamic term determines the acidity.